the definition of momentum, okay? And I cannot define to you the momentum of objects that doesn't have mass for photons. That's really complicated. You will see how we do that in 3C. What I can do is define, so the definition of momentum, be careful, is momentum, there's a fine print, is momentum of objects with mass m. Okay, so if it does have a mass, then momentum is defined as m times v. Okay, so first of all, we use p for momentum. Don't ask me why. And if you start asking why physicists choose a certain symbol, you will go down a rabbit hole that you never come back up. So also, well, m is taken, so p is sort of the next sort of closest alphabet to m. So all right, so p for momentum. There might be some Latin root from that. If anyone find out in the Google, let me know. So also v is a velocity. So momentum is also a velocity. M is a scalar that way. Okay. So any object with mass, if you want to write this in words, you can just say momentum is the product of the object's mass with its velocity. If you want to write it in equation, just make sure you define m is the object's mass, v is the object's velocity, and p is the object's momentum. Okay, simple definition. In some sense, if you try to get an intuition of it, maybe it's a little bit abstract, but again, the way to deal with abstract concepts is forget about the abstractity, right? Just cover that up and say, hey, this is a concept that's useful. The mass times the velocity of the mass of the object times the velocity of the object is going to be a concept that's going to be useful. You will see in a second, right? How it's going to be useful. And I hate keep writing MV every time because we're lazy, right? So if you're a lazy person, you should be happy in studying physics because now we will invent a new symbol. So I can write P instead of MV. So that's all what definitions are, right? In some sense, another way of saying is you introduce a new symbol in terms of old symbols. That's what you always say, right? That's what definition is. That's how definitions are different from formulas. Formulas are not definitions. Definitions are not formulas. Formulas are when you relate old variables to old variables. In some sense, for example, that's a formula. And definitions are always true. Formulas are not necessarily always true. It's a relationship between the variables a lot of times in a certain special case. Okay. Anyway, so that's the definition of it. If you want to gain some sort of intuition, just think of it as if an object has more mass, it has more momentum. If an object has higher velocity, it has more momentum. Okay. So momentum is a good word to choose because that even in everyday English, like not as a jargon, but everyday English, we kind of have a vague idea of what momentum is. You drive a truck, you have a high momentum. If you drive a very lightweighted car, then it has less momentum. So in a collision, which one will win? The one with the larger momentum will win. So we kind of have a vague idea, and it kind of matches with this intuition. Okay. All right. So with this in mind, now we can think about this. So now we will propose that the upgraded Newton's second law, reads this way. So the net force is not going to just change the object's acceleration, but it's going to change the object's momentum. Okay, so net force on the fine prints here on an object will change the momentum of the object. And this is the upgraded Newton's second law. Okay, so if you want to write that in words, you say any external net forces will equal to the rate of change. So get used to whenever you see ddt of something, ddt of some quantity in physics, it's rate of change of the momentum of the object's momentum. Okay, so you can say that. So how does that relate to the old version of it? And I think you can see how we get that, because dp dt means dmv dt. Okay, so we are differentiating with respect to time momentum. So momentum is the identical to that, right? So this is an identity. It's just by definition. And if the mass stays constant throughout the motion, throughout the acceleration or throughout the velocity, the motion, then you can pull it out of the derivative. Okay, and what's the rate of change of velocity? That's just ma. So rate of change of momentum is ma if m is constant. This is, right, a big if over here. So now, which one is more general? You can see this is more general. And in the special case where m is a constant, this will hold. And most of the time, when the object roll down a slope, right? Well, let's say when you go skiing, and let's say you go to Big Bear and you go skiing, you ski down the slope. Hopefully you don't lose a limb, you don't lose a leg, you don't lose a hand. So your mass stays constant, and that is just fine for you. But if you do start losing, I told you physics examples are violent. If you do start losing mass throughout that process, then you have a more complicated relationship. You will find yourself accelerating faster, or with the same amount of force, you will sort of go faster because you have a change in mass as well, right? So we now have a more general version. You can call it generalized Newton's second law. Okay, so we have a more general version of what does force do. Force changes an object's momentum, not only its velocity. Okay, so we will so this is the main concept. We also will introduce one more useful idea, is called impulse, is how much the momentum changes. It basically is really just a change in momentum, okay? And it's also related to how much force you apply on something in a given time, okay? So we'll make one more definition. We'll see some of the usefulness in practical situation in a second. So this is a new term, impulse, okay? So usually it's an impulse of a collision, okay? So impulse is defined, we use a symbol J. Again, don't ask me why. Well, I is actually taken. As you'll learn in 3B, I stands for current, electrical current. Nor does current start with an I. So don't go put yourself in that rabbit hole of asking these symbols. Some books do use I, but every book uses I for current. So some book makes a choice of, hey, if I'm later on using I for current, let's use something different for here. J is another very common one. And that's really the change in momentum. So since momentum is a vector, the impulse is also a vector. And of course, change in momentum is defined as the final momentum of an object minus the initial momentum. So how can a momentum change? Well, if the mass change, it will change. If the velocity change, it will change. If both change also, of course, P will change. Okay, so there's immediately that you can see that if there's a relationship between the impulse and force, because if we have a constant force, if F is constant, then in some sense, this is the instantaneous change in momentum with respect to time. But if F is constant, then if this is identical to dp dt, then it's also the same as the average rate of change. So if this is a constant, that's important. If it's constant, then the instantaneous change is the same as the average change. We've done this many times in kinematics. And now you can rearrange this. So this implies that change in momentum is equals to the force applied over the given time taken. So this is time taken. Okay. what's happened? So I'm talking about collision. Let me put back in my vectors properly. Force is a vector, momentum is a vector, time is a scalar, vector, vector. Okay, and obviously this is by definition J, and so you can also write J equals to F times delta T. So impulse is also F times delta T. So what is this concept is momentum is talking about collisions, right? So when something collides, let's say you have a ball, you bounce on the ground and it bounces up, right? Did the momentum change? Well, the mass didn't change, but the velocity changed, right? Initially, the velocity, let's say I'm going with this is positive. The velocity, let's say, is, let's say that's the positive x direction going up. Initially, let's say it's -2 meters per second. And after the bounce, let's say it's 2 meters per second. It's positive 2 meters per second. So the velocity changed from -2 to 2. So there's a change, right? There's a collision. So if I want to find out how much force there is over in this, how much force did the floor exert on the ball, so the force on ball by floor, then you just need to measure how much time did it take for this to change. So if you realize, oh, it's 0.1 seconds that bounce happened in, right? Just a fraction of seconds, just in 1/10 of a second, it changed from this to this. Okay, so if the time taken for this collision is 0.1 seconds, then you can calculate what is the force on the ball by the floor. Okay, so you see already there's a usefulness to the concept of momentum, and yeah, we will look at that more properly with some proper examples. Okay.